Hi, today we are going to discuss something called the mean value theorem and Rolle's theorem. You might recall earlier this year that we talked about the IVT, and this deals with functions or function values. And today we're dealing with the MVT. Now you might recall that the intermediate value theorem, it guarantees at some point we have to cross a certain value. For example, if I'm driving my car from 50 miles per hour to 60 miles per hour, at some point my speedometer has to read 50 miles per hour. That's the IVT. Today we're going to deal that with like average speeds. So today we're going to be doing the IVT but dealing with derivatives. So the where the IVT will deal with slopes, the mean value theorem, the MVT, deals with the derivatives. To give you an example of the difference, I can show if my speedometer goes from 50 miles per hour to 60 miles per hour, at some point I crossed 55 miles per hour. The mean value theorem says, well, if I know my average speed is 60 miles per hour, at some point my speed had to also be 60 miles per hour. And we can kind of see that right here. As I said, it's basically saying if my average speed is 60 miles per hour, right? At some point, we don't know where, at some point my instant speed also had to be 60 miles per hour. And that's how cops used to get you, by the way, get you speeding tickets before the advent of speed guns. So, to give you an example, like let's say we have a function right here. We have values at A and values at B. If I draw a secant line connecting these two, I can find the slope of the secant line. This would give me an average slope on A to B. That would give me an average slope on A to B. That would be like my average speed of 60 miles per hour. If I'm starting at time A, I'm ending at time B, I can get my average speed. What the mean value theorem says, well, if my average speed is 60, then there must be a point on the actual graph itself that also has to have that same speed of 60 miles per hour. And that's right here. Here we have a tangent line. The tangent line, this gives us our instant speed. And if you notice, at some point on that graph between A and B, the slope of the tangent line, the instant speed, will equal the slope of the secant line, our average speed or average slope here. And where this occurs, it will occur between A and B, just like kind of like IVT. So what we're saying here is at x equals c, we are saying that the tangent slope equals the secant slope. And this is one of the biggest concepts in calculus. We're going to spend a lot of time on this, okay? So sometimes people will say this, that the mean value theorem is the IVT for derivatives. And that's actually very, very true. They're kind of the same thing. One deals with functions, the other deals with derivatives. So to get the definition, just like IVT, we have to verify this all the time. So for the definition of MVT, we say, one, the function has to be continuous on a closed interval, must be closed. And differentiable, remember the derivative must exist on the open interval A to B. So differentiable, so no cusps, no corners, no vertical asymptotes, nothing like that, no jumps, anything like that. And it's going to be open, you might remember this, because the derivative does not exist at endpoints, no endpoints. So it has to be open. If the function is continuous and differentiable, this is what the mean value theorem says, then there's at least one number c such that, and this is what it says, the derivative of the function the derivative is equal to the slope. Remember, this is just my slope formula there, f of b minus f of a over b minus a. In other words, we will say that the slope of the tangent line equals the slope of a secant line. And you might remember, a tangent line is 1 point, the slope at 1 point, and the slope of a secant line is the slope at where we need 2 points. Other implications of the mean value theorem, this is what it kind of tells us, is that the tangent line is parallel to the secant line. Funny joke about parallel lines. Here's the funniest math joke you will ever hear. Okay, funniest math joke ever. Imagine you find yourself at a math conference. I promise you they're not the most exciting. So you find yourself at this math conference and you want to liven it up. Just stand up and tell this joke. Two parallel lines meet on a plane. Do you get it? They're parallel lines. They don't meet on a plane. You'll have them rolling in the aisles. Funniest math joke you will ever hear. So we know that the tangent line is going to be parallel to the secant line. We saw that in our graph up here. And two, that the instantaneous rate of change, this is what I like and the AP likes, the instantaneous rate of change, we've talked about that before, is equal to the average rate of change, AROC. And that's what this is. The instantaneous rate of change is your derivative, f prime of x, equals the average rate of change, f of b minus f of a over b minus a. Very easy to do. So let's go ahead and take a look at an example. Show that the MVT applies. Now, anytime they say the phrase MVT, all you have to remember, AROC equals IROC. That's it. MVT, AROC equals IROC. That the slopes are equal. That the slope of my tangent line equals the slope of my secant line. AROC equals IROC. If it does apply, find C. Where does the MVT hold? So we're going to do a little bit of a graph on this one just to kind of show you. If I were to graph this parabola right here, we're only interested between 0 and let's say 4. And if I graph my parabola, there it is, not drawn to scale, right here, I can get their values. At 0, we're at 1, and at 4, we're at 17. I know that, Mr. Werner, you didn't draw it up 1. What do I say? Not drawn to scale, right? All right, so what the MVT says, if I want to find out the MVT, what I'm going to do is I'm going to find first that secant slope, the slope of my secant line. And I can do that pretty easy. Rise over run. So it's going to be 17 minus 1 over 4 minus 1. Whoop, minus 0. Sorry about going to 0. 4 minus 0. And that's going to become 16 over 4, which is 4. So this is saying my average slope is 4. So what that tells me is my average slope is 4 somewhere on that graph, probably right about here. At this point right here, my slope of my tangent line also must equal 4. What we have to do is find out, well, where is this? And that's the goal. We want to find out where that occurs. So to do that, we do the mean value theorem. Now, the mean value theorem is kind of like IVT. You do have to show continuity and differentiability. You don't have to prove it. You just have to make sure that you acknowledge it. You would say f of x is continuous on, make sure you name the domain, 0 to 4, and differentiable on the open interval 0 to 4. Start out sentence. The function is continuous on 0 to 4 and differentiable on 0 to 4. Therefore, the mean value theorem applies. And somewhere on the domain, now open or hard is always a debate. Some people are like, you gotta make them closed, you gotta keep them open. It's always up for debate. I like to keep them open because we are talking about derivatives here. That somewhere on that domain, we would say the slope of a tangent line has to equal the slope of our secant line. And that's what I'm going to write. It's a sentence. It's a long one, but hey, not like stats, right? So that's part A. So we showed that it applies. The function is continuous and differentiable. The MVT applies, and it tells us that somewhere our two slopes are going to be equal. Now, this is the only time I say slope of tangent line is slope of secant line. I typically use IROC equals AROC. So to get the slope, so now we have to find where this occurs. Well, to find out where, I look at my tangent. So my slope, I'm going to take a look at my slope of my tangent line equals the slope of my secant line. Well, the slope of a tangent line is my derivative. My secant line is f of b minus f of a. So f of b is 4 minus f of a, which is 0. Right? There's my a, there's my b. All over 4 minus 0. So I take my derivative, which is 2x, equals, I already know the slope of my secant line. I did it up here. It was 4. Right? Remember, this was just 17 minus 1 over 4 minus 0. And I can divide. X equals 2. So this says at x equals 2, the slope of my tangent line equals the slope of my secant line. It's kind of like saying this. If I'm driving and my average speed is 60 miles per hour, when was my speed equal to 60 miles per hour? This allows us to find it. All right, go to part 2. We're going to talk about the Rolle's theorem, which is very similar. I did add there are a few more videos, some more examples on this if you want to check them out. I'll see you soon. Bye-bye.